In this example, we're going to use convolution to solve an ordinary differential equation with an unknown or general forcing function. That forcing function f of t is what makes this interesting. We're going to start by taking the Laplace transform of both sides of the differential equation. In this green box, I put down the formulas for the Laplace transform of the derivative of a function. We're going to start by using this formula right here. Y double prime of t is s squared capital Y of s minus s times little y of 0 minus little y prime of 0. Those are our initial conditions, plus the Laplace transform of y, which is capital Y of s. And then on the right-hand side, we have the Laplace transform of little f of t, and that is capital F of s. In step 2, we are going to substitute in the initial conditions. Here are our initial conditions, and if we look back up top, these initial conditions are equal to 0. So this makes this nice. We're just going to substitute in that those are 0, and we get s squared capital Y of s plus capital Y of s is equal to capital F of s. In step 3, we're just going to solve this equation for capital Y of s. We can write this as s squared plus 1 capital Y of s is equal to capital F of s, and then we get capital Y of s is equal to capital F of s, all divided by s squared plus 1. In step 4, we're going to use convolution to take the inverse Laplace transform of y of s to find y of t. Little y of t is the inverse Laplace transform of capital Y of s. So this is the inverse Laplace transform of f of s all divided by s squared plus 1. And we're going to rewrite this and break up what's inside, and we're going to write it as the inverse Laplace transform of capital F of s times 1 all divided by s squared plus 1. Convolution tells us that the inverse Laplace transform of the product of two functions, capital F of s times capital G of s, is the integral from 0 to t, f of tau, tau's just our dummy variable, times g of t minus tau d tau. This function right here, over here on the right, is capital G of s. Notice that inside our integral, we need little g of t, or little g of t minus tau. So what we're going to do first is find the inverse Laplace transform of g of s. This is the inverse Laplace transform of 1 all divided by s squared plus 1. And you might recognize this. This is just equal to sine of t. Now we can go ahead and just write down our solution. Our little y of t is the integral from 0 to t, f of tau. That just goes in as f of tau, times g of t minus tau. G of t is sine t, so we're going to replace t with t minus tau, and we get sine of t minus tau, and we integrate with respect to tau. And this is the solution to our differential equation. No matter what f of t is, this convolution integral gives us y of t. That's the power of convolution. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.